Alright, so hello everyone. My name is Viraj, and today we'll be discussing all the problems from the Leetcode Contest Weekly 414. Alright, so this is going to be a post contest discussion. Let us begin. Alright, so first four problems. Problem number one, convert date to binary. Alright, so you are given a string date representing a Gregorian calendar date in the YYYMMDD format. Alright, as in they also have the dash in that format. So basically, you are given a date, very simple to understand. And this date can be written in its binary representation by converting year, month, and day to their binary representation without any leading zeros. So, very important. And writing them down in year, month, day format. You will have to return this binary representation of the date. Now, the question is very simple. If you are familiar with how normally bits work, all the question is asking you to convert an integer to a binary format. That's all. So if I look at the problem example cases over here also, let's say the date was 2080, that is 2080 year. Then you have 02, that's the month. Maybe 02 can be February, and then 29. So 29 February of the 2080 year. They're just simply going to take 2080 as a number, convert that to binary. So in binary, this represents as 10000, 10000, and then 02 as in the number 2 will represent as 10, 29 will get represented as 11101. And then they just cumulate everything up with the dash format as expressed in the main date also, and just print it out as, I think, a string. So they have made sure that the date that is given to you, each and every date has 10 length, and they're also making sure that every date of 4, that is date of 4th index and date of 7th index, is a dash, which represents this middle dash that is coming to separate that year, month, and day. So the input is very simple to understand and very easily sorted by them also. You don't need to think about what can be the if and else cases in that part. All we have to do is extract the year, extract the day, extract the month, and get that running in a binary format, just represent it back, and I'll be good to go. Alright, so the problem is, as expected, a very very simple, easy problem, since this is Leetcode problem 1. So let us try to discuss this in a very pseudocode format. Let's say I have this y, and then I have dash mm, and then I have dash dd over here given to me. So what I would want is, let's say I have some function, let's say some like a void sort of a function, or let's say just a function call, which takes this as an integer n, and then inside this I'll try to do the binary representation of this particular number n and add that to some string, maybe an answer string globally declared somewhere. That's what I want to do. So just let's say I have a function that I've written neatly inside this. What I would want to do is, essentially I would want to take this string one at a time, like string at a time once, and then I would want to extract the year, the month, and the day in integer format. So this is all about the knowledge of STL libraries. What we can do is, I know this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I can maybe extract this string from 0 to 3 index. I can extract the string from 5 to 6 index, and I can extract the string from 8 to 9 index. That is going to give me individually the year, the month, and the day. So this gives me year, this gives me month, and this gives me day. But remember, this is in string format. So to convert a string to an integer, I can simply write an stoi function, that is string to integer function, and pass individually each of these strings inside this. So once I pass the year, the month, and the day, and this pops up to me the given n value that I want, which I can pass to this function 3 times, right? 3 times, so that I am able to get the binary representation of the year once, then the month, then the day. And then all I would want is to represent this in the binary context and add that to, let's say, maybe a string answer, and just add up those dashes also at the accurate places. So just a simple implementation problem. Now, giving a pseudocode for the beginners who might not know how we convert a binary to a simple number to a binary, or a decimal to a binary in that case. What we try to do is, we try to iterate in the whole number. So I'll say, all right, let me run sort of a while loop on n, right? While loop of n. And then what I want to do is, I want to see what is the last bit in n. So the last bit can be checked by various methods, right? Just to go for bitwise simple operation, last bit most famously can be checked by simply saying n and 1. This basically tells me the last bit's property. So n and 1 is kind of a check for odd and even. You can also write this as n mod 2, not a big deal. But this eventually would return to me the last bit in n. And if this bit is turned on as 1, that means I would be adding the character or string, you can say 1 in my answer, else I would be working with a 0 because that would represent it's a bit 0. And then I want to decrease n, as in I want to remove that last bit. So the very simple logic to remove the last bit is I will shift n I'll shift n right one time. And this is going to exhaust all the bits in n one by one from the right side, and eventually when n turns out to be 0, as in nothing is left in this case, I exhaust and I no longer am able to go inside the while loop. I come out, I break out of my while loop. And this helps because in the question it's given I don't want any leading zeros. So as soon as you exhaust n, you're not going to start representing or getting any more zeros or ones. I mean, ones are not possible anyways, but you'll not get anything beyond this, and you will exhaust until you reach the, I'll say this, MSB of n. Once you actually cross the MSB of n, n will turn 0 and you will not be able to iterate any further, which makes sense because I don't want any leading zeros in the binary representation. Alright, so I think this is simple enough to understand. All a simple implementation problem. For any beginner out there, I would suggest you simply can learn how do we convert decimal to binary. Very, very, very important algorithm for beginners. All right. And using this algorithm, you can actually solve this question in a very simple time frame, very simple implementation based property. I mean, you can also look up some STL function called as STOI, which helps you convert string to an integer. Maybe we can avoid that part also, just would be a difference in implementation, not a big deal. So I'll quickly show up how have I implemented the question, and let's see if we can get this part. So what I'm doing right now is I'm saying I'll extract the year, that would be STOI of date.substr from 0 to a length of 4. So in C++, the .substr function runs in such an order where I say first is the index and then is the length of the string I want to extract. So this technically means that if let's say I'm standing at index number 0, what I essentially want is I want to extract till the length, I'll say that like over here, let me rub this out. So from the index 0, I want to extract total of 4 lengthed string. From the index 5, I want to extract total of 2 lengthed string. From the index 8, I want to extract a total of 2 length string. So that is what I've written over here. Year becomes 0 to 4, month becomes 5 to 2, and day becomes 8 to 2. And I convert this from STOI, I receive an year, month, and date in the integer format. So this basically gets me 2080 in a number, 2 in a number, 29 in a number. Similarly, over 1900 in a number, 1 in a number, 1 in a number. Now I want to convert this day, month, and year individually in decimal to binary. So what I've done is I have first passed day, then the month, and then the year. Why have I done this? Because I am trying to represent the answer. So I'm trying to build my answer from right to left. All right. Just an implementation difference, seemed much easy. Otherwise, you might be forced to use some reverse function or something. I didn't want that complexity. So I would be going from right to left order. Right, I will try to build, because at the very end, it doesn't matter how do you build the string, it's just that you want the final answer. So I want to go from right to left. That's why I'll first process the day, then I will process a dash, then the month, then this dash again, and then this year. So that is what I've done. I will process the day, then I'm going to add a dash in the front of the answer. So how do I do that? I'll say I have this answer string variable publicly. I'll say I'm going to add an answer in the front and then concat the answer back from the end. I could have written it this like this, answer equals to answer plus dash, but that would have concated a dash. Let's say up till here, this is the answer. So the dash would have come at the very end, but I want the dash to come at the very start, because after I have processed the day, I want the dash over here, then the month, then the dash in the front again, and then the year. Hence my implementation difference. So I'll say, all right, I'll process the day, then add a dash, then I'll process the month, I'll add a dash again, and then I'll process the year finally. All right, great. I hope this is clear. Now, once I'll go towards the code of how would I process, very simple. As we talked about a general while looping, I'll take this integer n, while n, I'll say, is this last bit turned on? If it is turned on, then same thing, because I want to add from the left hand side, not from the right hand side. So I'll say answer equals to 1 plus answer, that is 1 as a character or a string, you can say as plus answer. Else the last bit is 0, so I'll say last bit 0 plus answer. And then what I'll do is I'll try to shift this n right one time, and this fully exhausts n. It is possible, and after you think that you cannot exhaust n anymore, you will simply come out of this while loop. So what is does this? It processes the date first, then a dash, then the year first, then a dash, and then the year, then the month and the dash, and then the year, and everything is done in an order such that I am trying to concat from on the left hand portion of whatever is the current updated string, because I basically want to create something like this: first 1, then 0, then 1, then 1, and then a dash, then 0, 1, then a dash, then 0, 0, 0, so on till 1. So just an implementation difference. Of course, you could have calculated this separately. Maybe you could have taken 3 variables, done 3 different binary strings, reversed them out if you were not reversing them, and so on, so on, so on. Why reverse? Why do I say reverse every time? Because it makes sense that when I would be calculating the bits, I am calculating the bits from the right to the left, right? For a binary representation. But eventually, since you want to print your answer like this, you would have to reverse that part. For all the people who are much familiar with how do we convert decimal to binary, this makes sense. But because I don't want to go into that part, I just used a simple trick by concatenating the character on the left hand side directly rather than on the right hand side, and this makes sure I don't have to use any reverse or any sort of a function. Alright, so very simple and implementation based problem. If you'll run a few test cases on this, you will quickly understand this. Let us try to submit this out and see what happens. I think I'll get the right answer. Of course, accepted. Alright, great. So now what else discuss is the time complexity. Right, so now stoi function, if you're using it, it has a time complexity, very simple time complexity of how much string are you passing inside this part. So if I'm passing a 4-lengthed string, I'll get a 4 complexity, 2-lengthed string, I'll get a 2 complexity. So I can maybe say that this is somewhat in like a constant order only, like I have maybe like 4 or 5 iterations to actually process this year part. Maybe I'll have something like 2 iterations to process this part, and maybe some 2 iterations to process this part, which is again very constant, considering the string is very small and the conversion will be very small. And now when I come to actually this part definitely takes up a time, and that time would be actually log base 2 of n. So I'm trying to exhaust the bits, and the maximum bits you can have would be in the order of base 2. So when this number gets exhausting, this is going to happen till every bit gets exhausted to the MSB, which can be set as log base 2n. Very simple to understand, that where n would be the number you actually pass inside this. So eventually, if this is almost constant, like I don't want to bother about this, but this can be a problem. So if I look at over here, the highest year that I can go is basically like I can maybe have something like 9999 year. That would be the highest number I can process, and that would again have maximum of like maybe if I try to represent this, maybe like maximum you can say maybe around I think 15-16 bits, not I think more than that. So the base point being is, no, I think into 2 would be, yeah, exactly like 15 or 16 bits maximum. So I can say that in a very simple order that this would run maximum in 20 iterations, because that is the highest time you would require to actually completely exhaust n overall, right? Maybe this also may be in approximately 20 iterations, and also this in 20 iterations. To be a very safe side, you can simply say that I am not going above the integer limit. So you can say this is highest and integer case, like maybe 31 iterations or 32 iterations to be very specific. That's like the highest integer limit. We have 2 power 31, but I know I'm not having a number that is in 2 power 31 order anyways. I'm having something very small than that. So I can maybe, I've just written a very high level order to this. To be very specific, maybe you can just calculate what would be the log 2 base of n and 9 and n and 9. I think it would turn out as like approximately I think 14 or something, to be very specific. So maybe I can have lesser approximation to this. I think 2 power 15 would be a decent one. Oh, 2 power 15 is also so much. So 2 power 10, so 14. Okay, 12, and then I have 13. All right, so I think 14 would be a good approximation. Correct. 16,000 something. 13 is approximately to 8192. So I know I can go to 2 power 14. That would be a decent case. So 15 is a decent general approximation for this. Maybe I can have 15 like this. So overall, the time complexity is almost next to constant, because such small iterations is something we don't even try to bother if it's highly constant. But I can simply say it's dependent on log base 2, right? Log base 2 n. Whatever highest number you pass inside this n part, it's going to approximately take that. Worst case would be like 15, 16 iterations. That's max. Very, very simple. Not going to give me a TLE at all. What about space? Am I using any extra space? I'm just using constant time to actually constant variables over here. So I don't consider this as space, extra space. So that's why I can say that I can have a space of, I think I should say constant. That would be fine. Maybe you can take up a space for the string answer which you're trying to return. But again, not a lot of bother with that part. So maybe like O of log 2 of n, that becomes the time complexity, and space can be written as simply the string size. So maybe I can call this as like answer size, whatever x approximately goes to the answer limit, right? Answer dot size. So again, a very like general approximation on time and space. Simple and easy enough problem. Only catch was, if you know how to convert decimal to binary, you will be good to go. All right. So let me submit this out, and yeah, great. So now let us begin up with the next problem, second problem of Leetcode. Maximum score of numbers in ranges. So a very, very fun problem, a very intuitive problem to understand. So you are given an array of integers start and an integer d representing n intervals, that is start of I comma start of I plus d. All right. So I have the start integers and then d. So it's basically a range. All right. Now I have to choose n integers where ith integer must belong to the ith interval. All right. Now the score of the chosen integers is defined as the minimum absolute difference between any two integers that have chosen. You have to return the maximum possible score of the chosen integers. All right, great. So the question basically asks you something like this. So in this case, let's say the first test case, you are given 6, 0, and 3. So what they'll say is, if d is a value that's given to you as 2, then you have the possibility to choose, like these are 3 positions you want to fill. The first position can be filled with any number from 6 to 6 plus 2, that's 8. So you can have the possibility to fill it with 6, 7, or 8. Similarly, this number can be filled either with 0, 1, or 2. And then this number can be filled with either 3, 4, and 5. So let's say you choose any such number you want to fill. Let's say I pick up 7 over here to fill. So this is 7. Let's say I pick up 1. So this is 1. And let's say I pick up, let's say 3. So this is 3. Once I do this, any pair, once I do this, I would be forced to calculate the score. And score would be, what would be the score? First, I'll say I will calculate the absolute difference between each and every pair of integers. So I'll say, okay, take up 7, 1, 7, 3, 1, 3. That's all the 3 pairs that are going to form. So 7, 1. Absolute of I shall say 1, 3, and then absolute of, let's say, 7, 3. Once I do this absolute difference, I receive some values. So in this case, this is 6, this is 2, and this is 4. Out of this values, I take the minimum. So the minimum out of this is 2, and this is my score for the current chosen numbers created like this. Now this score is currently 2. I want to maximize this score. I want to check whether I can create, I can create a very high score, and I want to print that highest possible score. And the argument is, like in this case, when I took a score to be 2, the argument was we can actually create a score up till 4. How? Let's say you take up actually 8 over here, you take up actual 0 over here, and you take up 4 over here. So the numbers would be 8, 0, and 4. And once you calculate the net difference on all the 3 pairs, it would turn out at 8, 0, this would be a difference of 8. 8 to 4, a difference of 4, and 0 to 4 is difference of 4. Now take the minimum out of this becomes 4, and 4 is the score, which is the highest score possible. Alright, so very, very simple problem to understand. Now the argument is that how do I actually calculate this score, and what is my general intuition? So my intuition can first of all also build from the time complexity, like expected time complexity, so I'll try to look into that part. You have the start length, that is the array size length as 10 power 5. Which is very, very high. So you of course cannot at all take this case where you actually create some solution of n square order. So in a 10 power 5 complexity, the general experience, by experience complexity I remember which I can implement is, maybe I can go in n, maybe I can go in constant, or I can go in n log n. So n log n complexity is also something that simply works in O of 10, 10 raised to 5 order. So these are like my 3 expected time complexities in my head. Now constant would be a very genius move, right? I don't know if I can create something like constant. Maybe I can create O of n, but n log n is also a highest range I can go. So I'll first start to think, okay, can I create something in n log n? Right? And because I get an intuition that maybe I can create somewhere in n log n, I start running my mindset towards what algorithms falls in n log n picture. All right. So this was my first intuition, and I kept it aside. Okay. In my head, I was like, okay, somewhere n log n maybe can work. Now let's move on. Let's try to think something else. Let's try to have some observation in this part. So of course, you're taking minimum in all the 3 numbers, like minimum out of all the pair caused differences, absolute differences for the numbers you chose. So let's say the numbers you chose were, let's say, A1, A2, A3, A4, and so on. So now it's very obvious, like let's say if I sort this array, and I know A1 is now the smallest, to A2, to A3, to A3, A4. This is like an increasing order. Now, if I tell you, calculate the absolute difference, so you will say, okay, one difference would obviously be like A1 minus A2. One difference would be A1 like A2, A2 minus A3. One difference would be A3 minus A4. That is very true. Now, I want to take the minimum. I know there would be more differences such as there would be A1, A3. Then there would be A1, A4. Very nice, fine. Then there would be one thing as A2, A3. Sorry, A2, A4. And then there would be one thing, I think no, I've covered everything. So, these are these extra 3 differences which are also there. But do we think I'm concerned with these 3 differences? The answer is no. Why? Because understand this, that eventually I am trying to take minimum, right? Now, I know that if this array is in a increasing order, the difference of A1 to A2, A2 to A3, A3 to A4 are the actual differences which I'm mainly concerned with. Because anyways, like in this, if I calculate the minimum of these 3 differences, there is no possibility that the minimum of all the possible 6 differences is going to lie in these 3 numbers. Not at all possible, because I am taking adjacent differences which are already very low. And if you actually take not adjacent differences, as in the difference between A1 and A2, if let's say this is X, and difference between A1 and A3, let's say this is like, if let's say this difference is X and this difference is Y, then you know Y is greater than X or greater than or equal to BX, but definitely greater than or equal to X. So why do I need to talk about a difference which is eventually greater than the adjacent differences? No, because eventually if I would have taken a minimum on all these 6 numbers, these 3 numbers would have negated as, like these 3 numbers were eventually futile for me anyways, because these 3 numbers were creating a difference which was anyways very higher than the adjacent differences. So all I am actually bothered, observation number one is all I'm eventually bothered is the adjacent differences. Adjacent differences is what I am actually bothered, because I know that anything that is not the adjacent difference after I sorted the array is anyways futile, because when I take minimum, those numbers will get removed since they are creating differences larger than adjacent differences. So I am only concerned with adjacent differences. This is my observation number 1. All right. Now, once this observation is important, you can now understand that the problem is simply saying, if you choose A1, A2, A3, A4, so on, some numbers like this, and you try to sort after you have sorted them in some order, what eventually I want to do is I want to maximize max of min the adjacent difference. This is what I want to do. Max of min of adjacent difference. And this idea finally translates for me to run a binary search. Why? Because what I can do is, I know, like I'll try to understand this. Let's say the minimum difference that you are trying to achieve is, let's say 0. That's the L range. And let's say there is a very high number R range where you are, let's say maybe like an int max range of saying this is the highest I want to go. And let's say you select a mid. You'll select a mid. So you will be like, okay, I'm trying to check whether or not I can create a difference of, like whether or not I can place the numbers in such a way such that every difference, let's say this is D1, let's say this is D2, let's say this is D2, D3, every difference is greater than equal to min. If I'm able to do this, then I know that I would be creating the eventual difference. Like when I would have taken the minimum of all the differences, it would have turned out to be mid. So if I say that my argument is, can I create a mid difference? Can I create a mid difference? Can I create a solution like this which has all different minimum differences to be mid? If the answer to this is true, then can I argue that answer to everything, as in every possible mid before this is also true? Can I do that? Almost I can say like this is sort of a discrete binary search. Not I can argue that every mid would create that beyond the case, but I can maybe argue that in a different manner. What about in a different case? Let's say you are arguing that answer to this is, like let's say answer to this is false. As in you cannot create the differences in such a way such that each difference is at least mid. This is not min, this is at least mid. Then can you argue that you will be able to create difference mid plus 1, difference mid plus 2, difference mid plus 3? No. So if the answer to this is false, answer everything after this is definitely false. If I was not able to create, I was not able to create the array in such a way that every adjacent difference is greater than equal to mid. If I was not able to create such an array where every adjacent if difference was greater than equal to mid, then when I would take minimum of all such adjacent differences, I will never receive mid. And if I was not able to do this for this case, will I be able to do this for mid plus 1? No. Will I be able to do this for mid plus 2? No. For mid plus 3? No. So I know that this sort of gives me a monotonic structure. Up to a limit, there is all falses, and then there is this one accurate place, let's call this X, where the answer is true, and then before this discretely you can say the answers might be true. Not exactly I can say that I would be able to create this, but there is some sort of a bifurcation where you can say you have a monotonic predicate sense. You have a monotonic predicate nature in a discrete manner. And because of this part, a binary search makes sense. This is kind of I'll give you a problem name also. There is a very famous problem called book allocation problem. This is also the same logic behind that. There is one more problem. I think there's like a painter's fence problem, something like this. So all these 2-3 problems, or there is something like I think some fencing cows problem. All these are like famous binary search problems which are based on the logic of max of min or min of max, either way, min of max. And they argue the same way in a discrete manner, that if you are trying to create minimum adjacent differences, minimum adjacent goals for some specific array, when you try to do that, if you actually receive some answer to be false, above that is everything is false, because I cannot create anything above that, and up to a limit that's false, and then this first place where you actually receive a true, and that becomes your max out of all the possible mins. So this is the same argument, this is the same logic based on the problem once you understand what am I trying to do. So I'll repeat. First, we saw that although I was asked to create all the differences, all possible differences, the differences which were not adjacent don't matter to me after I sort. So this is observation number 1. And on this observation, now I have reduced the problem to a very standard binary search of a max of min sort of a problem, how book allocation problem or painter's fence problem, fencing cow sort of problem works, where I can now implement just a simple binary search with a checker function and see whether it's possible for me to create such an array to actually satisfy the logic of mid difference. Let's look at the checker function. What do I eventually want to do? Like if you have a mid over here, I want to see whether I can pick up some elements like A1, A2, A3, A4, so on, let's say. Let's say only 4 elements out of that chosen range I was actually taking, and see whether I can create every adjacent difference to be greater than equal to mid. If I'm able to do that, then I know when I take minimum of all these differences, it will turn out to be like in that case mid. So I know eventually this is my target. Am I able to reach that position? So how do I do that? How do I actually go about that part? Very, very simple. I'll say, okay, let me start off with A1. A1 can be fixed. A1 can be kept over here. That's the first number I chose. And then when I am standing at A1, I'll go to A2 and ask, is the difference between A2 and A1, is the difference between A2 and A1 less than mid? Is it? If this is the case, then of course A2 needs to increase itself. As in, if let's say A2 was at some particular range, right, a particular number right now, and then I have the margin to increase A2 to anywhere from A2 to A2 plus D. That's the margin I have. So if A2 is not able to fulfill its own condition that A2 minus A1 created a difference of less than mid, then I want this difference to go greater than equal to mid. That means I would want to make this A2 jump to some new number. Now, if I want to make it jump to some new number, my question would be which number? So the ideal case is very commonsensical if you think about. If I'm standing at A2, I know that let's say in this case, I'll take up some example. Let's say this is 3, let's say this is 5, and let's say this is 8. So now if let's say you wanted to create a difference of 3, so greater than equal to 3, that is the mid. So, and you can maybe increase your D is 2. So I know that currently 3 and 5, I know that 5 minus 3 is less than mid is 3, mid is equal to 3. So it's less than 3. Yes, 5 minus 2 is 2, 2 is less than 3, of course. So I need to increase this. I can increase this from anywhere to 5. I can increase from 5 to, I can go to 6, I can go to 7. That is all the 3 numbers I can take. Now the argument is, which number should I take? Should I try to take the number 6 or should I try to take a number 7? Of course, I can take number 7 also, and 7 will still create a difference that is greater than equal to 3 for this case. But why would I want to create 7? Think like this. If you take this 5 to become 6, then you know that you will create a difference of 6 minus 3 to be exactly equal to mid, and you will be good to go. But if you take 7, although you will create a difference greater than equal to 3 again, but the problem is going to be on the next number. There is going to be a load on the next number A3 to increase itself to a higher range. What do I mean by that? Let's look over here. If you take this number to be 6, let's say you take this number to be 6. You converted and you said, okay, fine, I have the range, I took this to be 6. Now again, same problem. 8 minus 6 is equal to 2, and 2 is less than 3. So you would have said, okay, increase this 8 to a range of, in this case, increase this 8 to a range of 9. Fine, good enough. But what about the case if you would have taken this as 7? If you would have taken this as 7, what would have happened is you would have wanted to increase this A3 number as 10. And greedily, this doesn't make sense. Because what will happen is, if you take up larger chunks of number initially, then that difference is going to be a harm to you when you move on. Because then A3 increases even further, A4 might increase even further, A5 might increase even further, and so on, so on, so on. So what will eventually happen is, it can come across a case where you're standing at a condition where even if now you increase the number to the highest limit, as in if the number is currently A and you make it A plus D, then also you will not be able to create a difference of D with the previous number, or at least difference of at least mid with the previous number. That is why greedily it makes sense to utilize only that much space as I am needed. If I would eventually fulfill the condition by making this number as 6, although I could have also made this 7, I will not prefer to do that, because that creates an extra load coming on the right hand side. If you will take up your pen and paper and draw some test cases, you will fully understand what I'm trying to say. And this is the same logic how we try to follow in book allocation and Pater's fence, that greedily I don't want to create an array number which creates a load further. If I don't want to make a load that goes out to be further case, then it makes sense that let me stop over here. Let me take up to a number limit which still falls in my case, and I am good to go. So in this case, 6 falls to my case. It makes sense that I should not go above 6. 7 would create maybe a higher difference to this part. So let's just stop over here and move on. And eventually trying to do this algorithm, as soon as I move on and so on, I know that I want to see whether there is a case where I'm able to exhaust the array fully. If I'm able to do that, I am standing at a condition of true. And anywhere in the middle, if I'm not able to fulfill my condition, if even after creating a highest difference, making the number go to its highest limit of a plus d, if I'm not able to still satisfy my condition, I would prefer to go to false. So this is the whole ideology, and this is how you can create a checker function and give back the checker function's result to your binary search. And using that, you can now, in this monotonic predicate state, you can eventually figure out where do you want to move, whether you want to move from left to right or you want to move from right to left. All right, great. So now that the problem is fully understood, it can be related to back allocation and so on problems. So you can definitely look into this part for the beginners, and you will get the logic very easily of what we are trying to create, what difference do we actually want to do, and why am I going for a greedy approach in this. All right, great. So let us look at the coding part and understand how I have tried to implement this out. You will take an L is 0, R to be int max. Why int max? Because like over here they said that the maximum every number can be 10 power 9. So I just took a number greater than 10 power 9. Highest better case would be int max to create in that difference order. I know a difference above this cannot be created, so it's a decent limit to take. And then the answer, then I'll sort this array A, run a binary search, create a mid, and then ask, is this right? Is this giving me a possible mid difference where I can create differences, adjacent differences to be greater than equal to mid? If that's the case, yes, this is a possible potential answer. Make it and then increase L to mid plus 1. Why? Because if at a specific location, if I am true, then I want to bring L to forward, and if I am false, I want to bring R to mid minus 1, because if I am false, I know all the right search space is useless, and if I am at left, I know all the left search space could have been possible answers, so let me just move on even further. Not a big deal in that part. Alright, so L equals to mid plus 1, else R equals to mid minus 1. And now how do we check actually the checker function? Take the array A, take the difference D and the mid. Now I'll run a loop from 1 to less than size, and then I'll ask, is this currently, that is in the current index and previous index, already greater than equal to mid? Is the difference already greater than equal to mid? If it is, fine, continue. Don't do anything, because if that's the case, why do I need to hamper my numbers? I don't. But what about the else part? Else, I'll say, is like if I increase array of index, that is A of index, that's the current number, by D, and then I subtract the previous number, if after incrementing my current number array of index by the highest possible limit, that is D, even if after doing this, the previous difference, that the adjacent difference between array of index and array of index minus 1 still goes less than mid, then do I want to go any further? This is the case where I can say false. If I am not able to take up a number and increase it to a limit of D, and even after doing that, if I'm not able to create an adjacent difference to go greater than equal to mid, then why would I even iterate further? I'll say return false. And if this is not the case, then what would I prefer? I can obviously make array of index of I to be any number in that range, but I would prefer to make it just that number which creates the difference for me. So that just that number to create would be array of index of I minus 1, that's the previous number, plus mid. That would create a difference of mid between array of index and array of index of I minus 1. And then if I'm able to fully exhaust the array at the very end, I'll return a true. Alright, so again, this is a very standard problem if you think, right? It's like a standard problems of copies of simple binary search max to min, min to max problems. So if you are experienced with these problems, you would have figured this out problem in a very simple sense, and that's why I think this is the second problem, because this is too standard otherwise. Alright, cool. So now let us try to understand the time complexity. Of course, this is binary search, so you can say this is going to run in log of n order or log of search space order in that case. In my case, search space is int max. Int max is approximately like a 10 power 9 number. So you can say this is like a log of 10 power 9 order, or 2 into 10 power 9 order to be very specific. And then what I can say about this part, the checker function is simply iterating on the array once. So this is basically n. So I can say that the overall time complexity of this is O of log base 2 of 2 into 10 power 9 order, 2 into 10 power 9 order, into n, where n now is in 10 power 5. 2 into 10 power 9 base 2 would approximately be like I think 30, 35, 40 iterations max. So you can say that this is approximately in a 10 power 6 order. 10 power 6 order, which is definitely good to go. I know n log n works. And what about space? I am using any extra space? No, I'm not using any extra space to create my answer. So I can say space is constant. So let us try to submit this and we'll see we get an accepted solution. Definitely. So yeah, alright, beats 100% actually. Fine. So I think the problem is now pretty clear. Again, as I repeat, a standard problem for the beginners. You should go through problems like this on binary search for the min, max and max min part, so that you get a clearer picture on how do we actually tackle problems like this, right? And the only catch initially was to understand that I was only bothered with adjacent differences. If that clicks you, this is a standard problem. All right. Cool. So let us move on to the third problem. Now this is a very, very interesting problem. Like this is a very interesting problem. Either way, it might seem this is very tough, but the logic and the lines of code are very small in this. So let us try to see. Reach end of array with max score. You are given an integer array nums of length n. Your goal is to start an index 0 and reach index n minus 1. All right. And you can only jump to indexes greater than your current index. Fine. The score for a jump from index I to index j is calculated as j minus I into nums of I. Fine. Return the maximum possible total score by the time you reach the last index. All right, great. So let's try to look at the problem. So I'll give you an explanation of the test case. So the test case they had given was like this, like let's say 1, 3, 1, 5, 1, 3, 1, 5. And initially you're standing at this position, that's the 0. And you want to go at this position, that's in this case n minus 1, that is 0, 1, 2, 3. So from here to here, jump over here, and then from here to here, jump over here. When you do this, this is index 1, this is index 2. What eventually you would do, you would say if the place that I jumped, that's index 1, the place that I came from, that's index 0, multiply it with the place that I came from's number. So the number at that index was 1. So this is into 1. So I'll say into 1. Plus, now next time, the place that I jumped to is 3. The place that I came from is the index 1. And the number at the place where I came from is 3. And this gives me 7. And this is the highest score I can form. So you have to do this. You have to stand at a place. You have to jump somewhere. When you jump, take the difference between the place where you jump and the place you came from and multiply it with the number kept at the place where you came from. That's A of I. Do that. Go on incrementing and create something like this. This is called the score. And maximize this score possible as you can, like create a highest score possible. And to do that, like write up a code, and this is what the problem is eventually asking you. I want to create as high score as possible. So let's try to generalize this. Let's say, just assume that let's say there are some sets of indexes you have picked up. Okay, so you are standing at 0 currently, and then you picked up some indexes where you want to jump, and then the final index is n minus 1. So some set of indexes you picked up. Okay, let's call this indexes, let's say I1, I2, so on, I1, I2, I3, I4, so on, so on, so on. Right. So just let's say I have maybe, let's say only 3 indexes. There are some 3 indexes I have picked where I want to jump. So what is eventually going to happen? Can I rate it like this, that I would want I1 minus 0 into A of 0. Plus this would be I2 minus I1 into A of 1. A of I1. Plus this would be you can say I3 minus I2. This can be into A of I2. And then the final, like if this is, okay, if this is the I3 is the final index that I jump, so this can be said as n minus 1 minus I3 into A of I3. This is what is going to happen. Correct? Now, in this case, if you look at the question, they have simply said you can only jump to indices greater than your current index. So you obviously start off with 0, then you picked up I1, I2, I3, I4, so on, so on. So all these differences over here, like I'll mark them in a different pen. All these differences, I1 minus 0, I2 minus I1, I3 minus I2, n minus 1 minus I3, all these differences are definitely positive. These are definitely positive, not at all a thing to think about, right? These are definitely positive. What I eventually want is somehow I'm able to maybe create A0, like pick A0, AI1, AI2, A3 in such a way so that these net individual multiplications increase by a larger limit. If I'm able to do that, I'm increasing my max, correct? Now let's try to think in such a case. Let's say you are standing at some place. Let's say I'll call this place as the ith index. And the number over here is A of I. A of I. Fine. Now in this I index, from this I index, you have I plus 1. You have I plus 1. You have I plus 2. You have I plus 3. You have I plus 4. So on, so on, so on. And then the final index n minus 1. So I'll just take up a simple case. Now if you are standing at A of I, what is the one thing you can do? The one thing is obviously you can jump from I directly to n minus 1. If you do that, eventually what would you do? What would be the ideology to say you are doing? You would have indirectly said, I am saying n minus I minus 1 minus I times I have multiplied a of I and I have added this to my answer. This makes sense. But I'll talk in a greedy sense now. Tell me, if there is a number that is between this I and n minus 1 index, let's say there is a number, let's say this number, let's say the number kept at a of I of 3, a of I plus 3, let's say this number. Tell me, if this number a of I plus 3 is actually greater than a of I, then do you think I should jump, I'll change my pen, do you think I should jump from I, that is ai, so the index I to n minus 1, or I can jump from I to I plus 3 and then I plus 3 to n minus 1? What would be much more feasible? Just think about this. Of course, the second option. Why? Greedily. Let's see. Let's say this is the index, let's say 5, this is 6, this is 7, this is 8, this is 9, and let's say this is 10 index, and then let's say this is 11 index. So look at very carefully. Eventually, this value is 11 minus 5 into a of I, which means 6 into a of I. What does that mean? Can you count these indexes? 1, 2, 3, 4, 5, 6. That means you are basically increasing your answer with a of I 6 times. So I can say that this is the 6 positions a of I is encapsulating. 6 position a of I is encapsulating. All right, good to go, not a problem. But what if I would have taken the second option, not the first option, but the second option? What would have happened? In the second option, you would have said 8 minus 5 into a of I, which is good to go. That means a of I gets added over here at this place, right? This is the array, so don't forget. This is like the array, so don't bother about this part. This is the array. This is the option 1 I want. This is the option 2 I want. So let me change my pen actually. I think maybe with green I will write, so that would be much more better. Or I'll write with blue. So this is option 2. In option 2, what would have happened is, in option 2, you would have said, okay, this one time I got a of I, because this is like basically saying 3 into a of I. So 3 times I want a of I, right? So this is this a of I over here, which got counted, this a of I which got counted, and this a of I which got counted. Now after this, if you would have taken the root 2, the next answer would have been 11 minus 8 into a of I plus 3. A of I plus 3, which gives you a of I plus 3 one time. 11 minus 3 is 3, right? So 3 into a of I plus 3. So this gives you 3 times a of I plus 3. One a of I plus 3. One time over here, and you can say this is like one time over here. All right. And not the last place. I think I took the last place by mistake. This is a typo. You don't have the last place over here. All right. So what has happened now? Just observe. Initially, you were able to expand your answer by 6 times of a of I. One position here, one here, one here, one here, one here. But now, like this is I plus 3, sorry. Now, you are able to expand 3 times a of I and then 3 times a of I plus 1. A of I plus 3. If you took the second option. Now, isn't a of I plus 3 greater than a of I? That was the base case to start with. If a of I plus 3 is greater than a of I, then which is better? Should I take this above root or should I take this down root? Will this down root give me a value greater or will this above root give me a value greater? Compare. Of course, if I take the blue root, then I will get a larger value because a of I plus 3 is anyways greater than a of I. So I will get a of I as the added answer also. On bonus to that part, I will also get some extra number which was a of I plus 3. So I will get that added answer, added space also in my answer, which is again greedily good for me. I want to create high answers as possible. So why would I not want to go to I plus 3 difference? So now when I have taken this example, remember, I have made the range segment of the final position that you land and the initial position start to be constant. Over here also you went from 5 to 11 eventually, and over here you are also going from 5 to 8 to 11 eventually. So the differences of how much do you add is same. So I have kept one factor as constant, that is this difference over here, I2 minus I1, I3 minus I2. All these differences I have kept as constant. I know they are positive anyways. What I am trying to picture is what number should I choose? So now on this logic, the same argument comes is, do I want to choose a number, or would it be beneficial to choose a number which is less than equal to a of I? If there is some number from a of this position I to the last position n minus 1, where if there is some number you choose which is less than a of I, will you want to jump to that? No, you will say, if I jump to that anyways, I will create a difference. I will create my net answer to go even less than that or maybe equal to that, but not greater than that, because anyways, I would be standing at a value which creates lower differences. So why would I want to do that? No. But if you actually find a value which is greater than a of I, then will you want to jump to that? Yes, you will want to jump to that and distribute a root into two segments, like this blue segment I showed. Distributed it two ways. I could have taken the red root above, but that only gave me 6 times a of I. But now I got 3 times a of I plus 3 times of a of I plus 3. And since a of I plus 3 is greater than a of I got larger case. I got larger max case. So greedily, what is the final solution? Greedily, the final solution is, if you are standing at some a of I, you would prefer to move to the just next greater element rather than jumping fully the array, and do this every time till you finally exhaust the array. So the argument is, if you are standing at a of I, jump to the next greatest element. Let's say the next greater element to this is I plus 3. Fine. Then the next greater element, let's say the next greater element was found as I plus 7. Fine. Then so on till you reach the very end of the array, and this is the very start of the array where you begin. So the whole problem now boils down to a greedy approach where I am trying to jump to next greater elements every time, and that is bound to give me the highest possible answer. Now, to argue this, let's actually look up some test case and we'll understand this on that part. Okay, so let's say this is 1, 3 and 5. So 1, 3, 1 and 5. Standing at 1, what's the next greatest? Next greatest is 3. Standing at 3, what's the next greatest? Next greatest is 5. Take these numbers 1, 3 and 5 and do your calculation. This is index 0, this is index 1, and this is index 2. So 1 minus 0 into 1, this is 1, and 2 minus, this is index 3. 3 minus 1 into 2, this is like 6. So 1 plus 6, this is 7. Am I good to go? Yes. Now what about over here? See, 4, 3, 1, 3, 2. Take this case. 4, 3, 1, 3, 2. What's the next greater? There is no next greater, right? I don't have any next greater to 4. So that makes sense that, do I want to go to a number lower than this? No. Do I want to jump to 3 or 1 or 2? No. Let me jump directly to the very end, because I did not find any next greater. So I'll be like, okay, last index is 0, 1, 2, 3, 4. This is index 4, this is index 0. Do 4 minus 0 into 4, and that gives me 16. Which makes sense. If I would have taken any root between this, I know because the number is less than 4, I will create lesser differences now. So why do I want to do that? I will create lesser answer now. Why do I want to do that? No, I don't want to do that. So greedily, it makes sense to find the next greater. In this case, there was no next greater, so jump directly to the very end of the array. All right. So now again, to better think this theory, it would be best if you are able to draw this up in some test cases, and you will figure out the problem very, very easily and very, very quickly. Alright, so let us look at the coding part now. So I've done a very small coding. So I've done this coding in just how I showed you this part, like this a of I addition. So what I'll do is I'll start off with an answer, my current number, that's a numbers of 0, and then I'll start with index 1. Now from index 1, I'll keep on incrementing my answer by current, and I'll take current to be maximum of current common numbers of I. So what does this make me do? Let's say I was at this index I incremented a of I in my answer, moved on, came to the next number. Let's say this number is a of I plus 1. Now if a of I plus 1 is not greater than the current number, so this current never updates. If it never updates, I still increment by a of I. Then I still increment by a of I. But when I land at a of I plus 3, a of I plus 3 is greater than a of I. So my current will get updated, and I will now get a number by which I will have to increment my answer by a of I plus 3, because now current is a of I plus 3. So I'll keep on incrementing by a of I plus 3, then again a of I plus 3, then again a of I plus 3, and so on. And then I do this when I fully exhaust the array. So it's basically simply saying, every time you reach a number, calculate the max out of it, compare it with the current up till here, that is the part. If it's more, update it because that's the mass function, that's what you're trying to do, and just keep on adding that current simultaneously parallel to the answer. So this basically helps me create that next greater element addition. You can of course do this with an implementation where you take some like a I variable and a j variable index and I, and you want to jump to the next jth element. Maybe you can even solve this with the stack, create the next greater element logic yourself using a stack, then jump directly. Anyways, where you want, it's not going to be a big deal. All right, just I thought of a very small logic part which eventually makes sense, and it does the same thing which I want to do. So now the time complexity for this, of course, a simple loop running in O of n order. So this would be O of n complexity. And what about space? Am I using any extra space? No. So I can say space is pretty much constant. And if I try to submit this problem out, I think I'll get an accepted, which is correct. Yeah, got an accepted. So I know that I am good to go. This is the correct solution. So I mean, a very like it is a greedy based problem, and this greedy based problem, greedy based problems only have this ideology if you're able to prove some commonsensical solution in your head that okay, greedily this seems to work, then greedy mostly works. If you're not able to counteract any either case, then it never works. And I did that part only. I fixated my one part of the variable, that was this differences and indexes, and I tried to, in a same segment range, judge from where to where I want to jump. If I distribute that part likewise, what will happen? And that gave me this greedy approach that okay, if I bifurcated my part to a place where I received a number greater, then that only helps me increase my answer even further. So, and if I don't find any number greater, then taking less than equal to numbers are not at all beneficial. It would simply, I'll be still happy to stick to my A of I number and move on and continue as forward as I can. All right. So that's all for the third problem. Let us move on to the fourth problem now. All right. So the final problem, maximum number of moves to kill all pawns. Let us see. There is a 50 cross 50 chessboard. All right. So not a very big chessboard with one knight and some pawns on it. Okay, fine. You are given two integers ky and kx and ky, where kx and ky denotes the position of the knight. The 2D array positions where there is xi, ya, that's the position of the pawns on the chessboard, and so on. And this is like a positions array. So there you have some number of pawns on the chessboard with every position given to you. Now this is a turn-based game where Alice and Bob play. All right, the famous Alice and Bob. Alice goes first. In each turn, the player selects a pawn that still exists on the board and captures it with the knight in the fewest possible moves. Now it's written, note that the player can select any pawn. It's not compulsory that he or she selects the pawn that is that can be captured in the least number of moves. As in, if let's say you have like 5-6 pawns, and let's say you know that, let's say this pawn is going to get captured in the lowest number of moves, then it's not compulsory you will choose that pawn. The only argument is you will choose some pawn in the non-captured pawns, and then if you have chosen a pawn, you will try to capture it in the fewest number of moves. So that's a very big difference that's given. So definitely read this sentence once more if you're not able to understand this. All right, again, as we go along the problem, we'll explain this part. In the process of capturing that selected pawn, the knight may pass other pawns without capturing them. Only the selected pawn can be captured in this turn. So if you are actually wanting to select some pawn, capture some selected pawn, and you, let's say, jump to a place where there is one more pawn kept, you don't capture it, because the argument is if I want to capture the selected pawn, I will only capture the selected pawn. So for that time being, you can imagine that all the board is basically empty and your only focus is to somehow capture that selected pawn. All right. So now Alice is trying to maximize the sum of number of moves made by both players until there are no pawns on the board, whereas Bob tries to minimize them. All right. And you need to return the maximum total number of moves made during the game that Alice can achieve, assuming both players play optimally. So basically, Alice tries to increase the answer, Bob tries to decrease the answer. Eventually, Alice will want to somehow maximize this, and I want to do that part. All right. Now, note that in one move, a chess knight has 8 possible positions it can move to, as illustrated. Each move is 2 cells in a cardinal direction, then 1 in the orthogonal direction. So basically, you can move standard how a pawn moves. You can move in the 8 directions. Okay, great. Now, if I look at the constraints, like even before you can look at the example cases. Let's say, okay, let's look at the example. So example 2, they've actually given you a good GIF play over here. So just by understanding the GIF, you can understand, okay, how is 8 moves coming? So if you are at this position first, we jump to this, capture this pawn. So it's basically 2 moves. Then we capture, I think, this pawn. That's 2 moves by Bob. Then Alice captures 1, 1 pawn in 4 moves. So that gives you a total of 8 moves. And that's the highest I can go. That's the highest that I want to go if the players may play optimally, and that's the argument. So let's not go into that part. I mean, assumably that the answer is correct. Let's actually look into one case is, if I actually have to think in the direction of solving the problem, specifically in hard Leetcode problem, I need to see the constraints first, because hard problems give me a hint towards the direction only. Okay, so first of all, constraints are something that's very small. So when I look at the problem, my argument was, okay, constraints seem very small. That means I can run some brute solutions also if necessity becomes the case. So I'll say, okay, KI, KY and KY were in 49 order. So basically you have a 50 cross 50 chessboard. That's a simple constraint. Now the positions are also very, very low. You have only 15 positions you are actually bothered with. That's the second argument. And then positions can range anywhere to 0 to 49. That's fine. And then all the positions are unique, and then KY and KX and KY are not belonging positions Y. That's a simple constraint. So anyways, if I look it like this, the constraints overall are very small. When I talk about constraints being very small, my argument is like this. So when you have drawn the chessboard, and you know you are at some, so I cannot draw, I think, a 50 cross 50 chessboard. So I'll just draw a small simulation of that. Let's say the chessboard is something like this. So, and let's say you have drawn this chessboard. Let's draw it a bit more, something like this. All right, very bad at drawing this chessboard. So yeah, cool. Something like this. Like I have drawn something like I should draw something like a 5 cross 5. Okay, I think this would be fine. So I've drawn a 5 cross 5 chessboard over here. Now the argument is that if you are standing with your knight somewhere, if this is K, and you are at some, like there are some pawn kept as, let's say like pawn P1 over here, like let's say pawn P2 over here, let's say pawn P3 over here, and so on. And then the argument that I want to play is Alice's. So can I argue this, that if I want to eventually increase the net number of moves, then Alice should also try to increase her net chances of moving the pawn. So again, remember, the first sentence is, if I select a pawn, I want to capture it in the fewest number of moves. So Alice is not going to bother if she has selected a pawn, how do I increase the number of moves after that? But initially, Alice has the option to choose some pawn. Very, very, very important statement. So that being said, if let's say I am standing with my K over here, if Alice somehow knows that the number of moves to capture P1, minimum number of moves to capture P1 is M1, minimum number of moves to capture is M2, and minimum number of moves to capture over here is M3. Then in all these three possible cases, if somehow she knows this, then can I say that I would have ran a possibility check on all these three sorts of captures? I would have first tried to capture P1 with M1 moves, P2 with M2 moves, P3 with M3 moves, and so on, so on, so on. And then even bifurcate it further to Bob's condition, to Alice's condition, and so on. This would have definitely helped me. But what is the initial argument? Initially, you should know that if you are standing at this position, then the number of moves to capture this position is M1, the number of moves to capture this position is M2, the number of moves to capture this position is M3. Now, if you try to calculate this in real-time order, it is going to be very tedious. As in, what do I mean by real-time? As in, you can say, if you are standing at this K, and then you are like, okay, let me try to run for M1, M2, M3. It's very futile. No. Think like this. Somehow, if I am able to pre-compute my some sort of a, let's say, some sort of a data structure which is going to help me answer the query that if you were standing at, let's say, X, Y index, and you wanted to go to, let's say, A, B index, assumably like this is the K knight and this is the pawn, then if moving from K to pawn P at the position A, B, what is the minimum number of moves? If somehow I already have pre-computed this, then will I be bothered about calculating M1, M2, M3? No. Will I be doing that? No. All I would be bothered is which pawn do I need to select next. Let's say I would say I'll select P2, or let's say I'll select P1, or let's say I'll select P3, and I will quickly call corresponding to P1, P2 or P3, whichever I select, the M1, M2 and M3 values, and I will continue forward. I'll make my knight jump, let's say at this position. Done and dusted. Now when a knight is at this position, again, if let's say the same question, if somehow I know the minimum number of moves to capture K, knight being over here, to this place, this would be like somewhere like M1 dash, because this has changed now. This is like something like M3 dash, because this has now changed from this new position, since K knight has position has changed. If I know this beforehand, then Bob, like I have exhausted Alice's turn now, then Bob will be good to go, because now Bob will try to minimize the number of net moves. But because you have already pre-computed M1 dash, M3 dash and so on, you will not have to pre-compute it every time from every position. That's actually the catch inside this problem. Alright, so now let's try to analyze this in such a way. What if I do this pre-computation, is it heavy for me? Am I able to do it or not? That's the question. So the pre-computation, what is the pre-computation? The pre-computation is you want to somehow capture from every x comma y to every a comma b as two pair of indexes on the board, what is the minimum number of moves. So if you want to capture like from x comma y to a comma b, what is the minimum number of moves, or vice versa is going to be the same. If like moves from x comma y to a comma b by the knight position is 3, then a comma b to x comma y will also be 3. So same thing. So if you are able to capture this data somehow, then you will be good to go. And let's think, how would we capture this data? So now the pre-computation problem is a separate subproblem. The problem is stating, starting at some source, calculate the minimum moves required to reach every cell on the grid using the knight sort of a move. Like you cannot move in any random direction or any random way. How a knight moves, move it like this in 8 directions, and in that knight move order, capture the minimum moves from source to all possible cells on the grid. Now this is a BFS problem on the grid. This is a very simple and very pre-computed BFS problem on the grid. I can use a queue structure in the BFS order, push this source in that queue, and start popping the queue every from the front. Keep a distance that's, let's say, initially 0. Distance as in how many, or not distance, I can say, maybe I can call this as moves as 0. Keep on incrementing my moves, and finally calculate for x comma y to every other possible iteration of case what becomes my eventual answer. And this actually gives me the pre-computed data structure which will help me to quickly answer the queries. If I was standing at some, like if it was Alice's turn and I was standing at some knight position, let's say this is x comma y, then from this x comma y position, if she would have taken p1 to capture p1, what were the number of moves? If she would have taken p2, what were the capture of moves? If she would have taken p3, what were the capture of moves? So then the main problem can be solved. But in the main problem, this is a problem which could have come every time. Every time you would have been required that if you were standing at some x comma y position, where if you want to jump to some a comma b position, what was the number of moves? What were the minimum number of moves? Every time this question would have come into picture, I will pre-compute it. So this definitely saves me some time complexity, or actually a very large chunk of time complexity on the larger picture. So now if I talk about this BFS computation, every BFS computation for each and every source cell is going to take n into m order. That's the number of rows into number of columns, because highest number of cells I would process is each and every cell. That's n into m. I have total n into m cells. And I am going to do this for every n into m cell, for every cell in the case, this BFS thing. So this is like the BFS call. I would try to encapsulate, and I would do this for every cell. This basically means that in worst case order, since I have a 50 cross 50 chessboard, I would have 50 power 4 complexity of pre-computation, which is eventually 6 to 5, and then I think this is 0, 0, 0, 0, which means this is somewhat like a 6 into 10 power 7 order. Now this is not very small per se, but then in pre-computation way, if you have a 10 power 8 limit at max, this is just on the borderline of passing. This will definitely pass, and it's not going to create a TLE havoc for me. Right? That means in a pre-computation of definitely some large order, but still good to go order, I can calculate for every xy to every ab what is the minimum number of moves. So I can create some sort of a distance vector, distance array of 50 size, 50 size, 50 size, 50 size. This total capacity of 50 cross 50 cross 50 cross 50, or basically 50 cross 4, will finally store answer of minimum number of moves for every processing I could have done. All right. So let's look, now that we discussed part till here, since this is a sub problem, I think I should show you the code part for the pre-processing, so that we can after that look into the main part. So this is the pre-processing I've done over here. Okay, I'll call this as a pre-function. Then I want to not pre-process it again because I've written this outside the class solution. So for every test case, I don't want to do this because for every test case, the answer is same. So why do I need to do that every time? I won't do it every time. So I have taken a process variable and I'll say, if it's initially false, I'll turn it later to be true. If that would mean I have already pre-processed. Now let's look into the DP. I'll create a distance vector of 50, 50, 50, 50, 4D array. All right, distance. Then all the possible combinations of moving for the night. So dx, dy, 8 combinations. That would be 1, 2 pair, 2, 1 pair, 2, -2 pair, 1, -2 pair, 9, -2, -2, -2, -1, -2, 1, and -1, 2. So this is all like the 8 directions basically. 8 direction, 1, 2, like this, 8 directions am I talking about. And these 8 directions would encapsulate this much position that I want to gain. All right, you can definitely cross verify or reference this from this positions over here. If you are standing at night over here and you want to move at this position, this is basically -2, 1. -2 in the previous row direction, 2 rows previously, and then 1 column forward. So this is -2, 1. Right? And such 8 combinations I have taken. Now this distance function. So in the pre-computation, what will I say? I'm going to iterate from every cell to every cell pair. So 0 to 50, less than 50, 0 to less than 50. Then if this is not already calculated, as in distance of I of j to I of j is not calculated already, then I'm going to calculate it. And during the calculation, simple BFS thing. I will create a queue for the current position, pair of current position and the distance. So I'll take pair of int, int. The first is going to be, this part is going to be the x, y, and this is going to be the distance. And then I'll push back start of x, start of y, and 0, because I know from this particular position, the current distance is 0. And I'll declare that, okay, this position to from x, from start of x to start of y to start of x to start of y, same, the distance from point to itself is 0. Now go inside the while loop of queue, pop x, y, and d, pop the whole output, whole front part from the queue, go in all the 8 possible directions, calculate a new x and a new y. Then ask myself, first of all, is this new x and new y within the range? Is it greater than equal to 0, less than 50, greater than equal to 0, less than 50? Good to go. And is this not pre-computed? Is start of x to start of y, as in standing at start of x to start of y, going to new x to new y, is it still -1? If it's still -1, that means it has not been calculated. So if it has not been calculated, I will make that value as 1 plus d, and I will push back d plus 1, that's the new distance, or 1 plus d simply. This can be written as like d plus 1 only, same thing. I'll update the distance and I'll push back the new x, new y pair, comma d plus 1 together as a pair in the queue to process the next coming queries. And this eventually is going to run in a BFS, like this is a BFS order which runs in n 50 cross 50 order, which eventually means I am calculating a BFS call in all the directions. Now, when this is done, I am going to do this for all the 50 parts. So like this is the for into for loop, and then inside this function. So this eventually tells me this is 50 power 4 sort of function, as I explained over here, 50 power 4, which is 6 into 10 power 7 approximately, which is 6 into 10 power 7 approximately. And since this is pre-computed, so I don't have any extra added time complexity which is getting multiplied into this. This is just a pre-computation I have already done. So if you can see over in the function also, I have like called this pre-computation, this function over here, and I'm pre-computing it. All right, good to go. Now let's come to the next part of the question. Now that I have pre-computed, what has eventually helped me? My help has been this much, that I now know if I am standing at some x, y position, if I want to go to some a, b position, what is the minimum number of moves? But now what happens next? Let's come to this part. Now you basically have 15 maximum. Look at the constraints again over here. You have total of 15 maximum pawns on the board. So you have maximum 15 pawns on the board. Okay. And you already have the distance that you want, and you have some variable that dictates that what turn are you at currently. So you are, let's say you are in an Alice's turn. So let's say this is Alice's turn means 1 and Bob's turn means 0. So maybe I can call this as turn. So you are basically on some turn sort of a variable which you are standing at, and then you are, and as I said previously, you have 15 positions to totally capture, and then you also have to choose which position I want to capture currently. Do I want to capture the 14th position? Do I want to capture the 15th position? Do I want to capture the second position? Do I want to capture the third position? When I say position, I mean by saying pawn. So like second pawn, third pawn, 15th pawn, 14th pawn. What do I want to do? Again, I have a lot of options. So this gives me sort of a recursive solution in my head. Why recursive? Because like recursive plus memoized later, because I would want a memoized solution. Why recursive plus memoized solution in my head? Because I know that I cannot apply greedy. Remember, when you are standing at some x, y position and you are Alice, although your target is to increase the number of moves eventually, the argument is you cannot greedily say that I would love to move to p3 or I will love to move to p1. No, you will have to explore all options. You will have to jump to p1, have to jump to p2, have to jump to p3 and call your function accordingly. You cannot greedily say that I would have to jump to p1 only just because I think maybe m1 was very large. No, because it can happen that later that moves fetches you an answer which is not right or which is much lower than what your expected was. So it's better or it makes sense that I would love to go into every such case ordering from a xy position to some possible positions which I can select out of which I can select one pawn and calculate the net answer according to with whether Alice's turn were there or Bob's turn was there. Alright, and to do this, I will obviously have to maintain something which helps me recognize that which pawn has already been selected. So again, remember this. I'll say a different question to you, and I think you are going to for every beginner or every general amateur guy is going to get this logic very quickly. We have seen problems where we call this problem like subset calculation. Calculate all possible subsets of some array. What happens over here is you say that, okay, if the array has, let's say 4 numbers, let's say the number is A1, A2, A3, A4, then I want to somehow maintain something which helps me say that, okay, have I selected A2 or not? Have I selected A4 or not? If I have done, fine. Now, can I select A1 or not? Can I select A4 or not? A3 or not? And so on, so on, so on. To do this, we use something known as bit masking. Where we call some variable, that variable is specifically called as a mask variable. All right. And that process is called bit masking. Where this mask variable, bit masking, where this mask variable helps me to maintain a information in bit format. So it's basically this mask is going to basically be a 2 power 15 number in a worst case scenario where let's say I have 15 bits. So it's going to help me store some information. And what is that information? That information is, if let's say this bit is turned on, this means that this pawn number has been captured. If let's say this bit is 0, then that means this pawn has still not been captured. If this is 0, not captured. If this is 1, already captured. If this is 0, not captured, and so on, so on, so on. So can I maintain this mask to finally argue that I would want to continue on any position of pawn that has already been captured and any pawn that has not been captured, as in any bit in this masked number which is 0. If that bit is 0, that means that particular location's position pawn has not been captured. I will try to capture it. I will turn this bit 1 and I will recurse further. And at the very end, if I am able to cover all the pawns fully and finally, then that would mean I have covered all the basic pawns currently, and that would give me the right, that would make me stop my recursion from the base case and return back. Alright, so this is sort of a bit masking question now. Since you have pre-computed in a BFS on a grid order, the number of minimum moves you would require to go from some x comma y, to some a comma b, the problem simply now becomes sort of a bit masking DP problem. recursive, you can create a recursive solution first, then memorize it, so it basically becomes a bit DP. And since we will be using something known as mask with this particular case of selected non-selected thing, it would be bit masking, to be very specific. All right, so this is not at all a very beginner friendly concept, but in bit masking this is a very standard problem. All right, it's not a very tough problem in bit masking, it's like a medium rated problem in the topic of bit masking. So if you are familiar with bit masking, you should definitely give this problem a try. You will be able to create this mask and turn on your own. All right, so now we can look at the code part and try to understand how can we actually do this bit masking order. All right, so this is the code. So we had already discussed the pre function, right? This was the pre computation function, and now let's actually look at the main function over here. So I will create a DP of 3 states, right? One is going to be the current position I'm standing at, one is the turn, is it Alice turn, Bob turn, and one is the mask, which is the information which helps me select or non-select and tell me, okay, this pawn is selected, fine. This pawn is not selected, okay, maybe run that option by me. Okay, so I need a 3D DP. I will first add the knight's position in the positions array. Why do I want to do that? Because I want to start off with the knight position and then move on further. So I will add that in the positions array only, and the new size of the positions array will become n. Then I will do the pre-computation as expected, and then I will resize the DP to be of the n size, to be of, so first I'm maintaining the cap position, that is total of n size. So this becomes, actually this would become something like 16 order max case, but then not a big deal, right? N. Then the second parameter would be 1 left shifted n times, that would be the mask. Why this much? Because this is basically going to be 2 part 16 then in that case, right? So you want 2 part 16, that means shift 2 or shift basically 1 left to 16 times. And then you will have the final state as the turn. So 2 turns basically 0 or 1, either it's Alice, either it's Bob's, and so on. And this is -1. Okay, so what I'm trying to do is, if it's 0, it's Alice's turn. If it's 1, it's Bob's turn. Simple conventional sort of implementation. You can definitely have something of your own. So then I will call this function, helper function, pass the first position, that's n-1, that's the position of the knight. Then I will turn on the mask to that part. So I'll say I'm going to pass a mask value which is 1 left shifted n-1, which means that the n-1 bit in this particular number has been turned on, and then 0, and then the positions array. Now I'll go in the DP part. You have the function, you calculate the n positions, that's fine. And then if you have already covered all the positions, then that's the base case, return back, which would mean that the mask value has become equal to, remember this number, it's 1 left shift n-1. What is the meaning of this? If you left shift your number, like if you do 1 left shift 16, right, 1 left shift 16, that creates something like 1 0 0 0, so on, so on, so on, so on. And when you do -1, this converts a number like this, 1 1 1 1 1 1 1, because this is the base case. Like this is the meaning of converting. And if you subtract from a 2 power number, if 2 power x, from 2 power x, if you subtract the number 1, then you get a number which basically means that all the bits before x, that is the bits to x-1 to 0, all will become 1. So that is what I eventually want. I want to see if I have turned on all the 15 bits after, like if this is the 16 bit, once this has been turned on, that means knight has been covered. Now after this, when I finally end my base case, that would mean every bit after this, that is all to 15 to all the less bits, have been turned on or not. If they have been turned on, then the mask value would be equal to that value, and I would return 0, because that would mean all positions have been visited. This is the base case. Then what is the result? The result is, if DP of current of mask of 10 is already pre-calculated, return it simply. That's the memorized case. Then I have an answer variable. If this is not the case, let's look at the logic. The answer, x and y, that's the current position, that's current of 0, current of 1, x coordinate, y coordinate of the current pawn, which I want to actually capture. Sorry, not the current pawn, the current position where I'm standing at. So the current position I'm standing at is x and y. Now I'll say, is it Alice's turn or it's Bob's turn? If not of turn means not of 0, not of 0 means 1. So if it's 0, that means it's Alice's turn. Alice wants to maximize the number of moves, hence answer will become int min. And then I will go to every possible position from 0 to n. I will ask whether this is already turned on or not. If it's already turned on, I will skip it, because that means this mask position ending with 1 left shifted to 1 gives me a number that is definitely greater than 1. If that is the case, then I know greater than equal to 1, then that means I want to continue, because this means that I am skipping this position. This pawn has been already captured, or the ith pawn has been already captured. If it is not the case, then I calculate the next x, that's position of I of 0, next y, that's position of I of 1, and then I get the new distance between xy, going from xy to next x of nest of y in simple O of 1 query. Remember, why you are getting this quickly? Because you had pre-computed distances from every possible xy to every possible a of b. So in this case, it becomes xy to xy, from xy going to next x of next y, the minimum distance is this. Now I want to maximize the answer since this is Alice's position. So Alice will say answer equals to answer of max of answer comma this number of moves, that's new distance, plus call this function again. Inside this, turn the turn to be not of turn. That means if it's Alice, now it's Bob's turn. Past positions as it is. The current position that you were becomes I, and then the mask will get turned on by I left shifted to 1 left shifted to I times. This would mean that I have turned on the information in this mask number. That bit has been turned on 1, which would eventually mean that yes, this pawn has been captured. Now next time in the next recursive iterations, if you ever think that that position is already turned, understand this, that pawn has already been captured, so no need to capture it again. Alright, and same logic will be captured for Bob also. The only difference would be that in this case, Bob will want to minimize the answer. So I will do the same thing, just I will run a min function and not a max. And then when I finally come out of this if and else check, I will say what is the current, I can say sort of a dp of, this would become dp of current of mask of turn of answer, dp of current of mask of turn equals to answer. This will save my state now, and so that I don't have to compute the states every time, basically creating a memoized solution for me. Alright, now what is the time complexity of this thing? Of course, the time complexity is dependent on states. So changing states are current, mask and turn. So if changing states are current, mask and turn, I basically have like, I will have 15 into like this can be in worst case called as 15 into 2 power 15. This much is already there. Inside this again you are running a loop, right? Which is again going to be in worst case 15 order. So you can say this is basically 15 into 15 into 2 power 15. Now 2 power 15 is approximately, I think this is, okay, 327. I'll multiply 15 into this and I'll multiply 15 into this. So this basically gives 737. 2800. So this is total, I think you can say 7 into 10 power 6 order. Now 7 into 10 power 6 order, like I can write this out like this, 7 into 10 power 6 order, which is as compared to the pre-computation. Our pre-computation wasn't 6 into, we calculate 6 into 10 power 7 order. So overall, the complexity, if you write the complexity, it's basically, you can say TC is like n into 2 power n plus 50 power 4, which is within my boundaries. It's not like I can say very, very good time complexity, but it's definitely just within the boundary of not getting a TLE. And what about space? I'm using some extra space. Definitely I'm using a 50 cross 50 cross 50 cross matrix over here. So you can say space is coming, one space is coming from 50 cross 50 power 4. And then this vector also, this dp vector also, which has 15 into 2 power 15 into 2. So you can call this as 2 into n into 2 power n. This is the space. So in like a very higher boundary limits, but still within my particular limit, I am able to fully get the answer. And if I submit this out, I think this should work. Let's see. So I think I'm good to go. Yeah, got accepted. Cool. So this is the whole and full and final solution. So I'll repeat the solution once more. First, I saw that I need, if I am able to stand at some xy position and I want to go to some a comma b position, this question that is from x comma y to a comma b, what's the minimum number of moves? It's getting asked a lot from any number of times. When Alice's turn will be there, she will also ask the same thing. When Bob's will be there, she will also ask the same thing, which means I need some pre-computation. So my first observation was I need some pre-computation on the board itself. That pre-computation would be, I can store from every x comma y to every a comma b, what's the current minimum number of moves. I did that part and I said, okay, pre-computation is done by simple BFS on grid logic. This is again a very standard problem. Once I was able to complete this check, now what I did was I went into the other logic where I said, okay, pre-computation has been done. Now what do I need to maintain in recursion order? First of all, can I apply greedy? Answer was no, because that is where I said, okay, if you are standing at with k knight, you will have to iterate and see what will happen if you go to P1, what will happen if you go to P2, what will happen if you go to P3, and so on, so on, so on. So you cannot do that part. You will have to go to every possible pawn. To do that, that means this is a recursion problem. And now recursion will definitely not work, so I need to memorize it later. So this creates and tells me I need some selection of pawn. I need pawn order to be maintained as a current position to be maintained, and what turn do I have? So that means I have the states ready with me, and since I am using a mask to maintain this information, this becomes a bit masking DP problem now. That's the main problem. So after the pre-computation, I will use bit masking DP. I will make my 3D array, go into that part. If it's already pre-computed, return it. If not, go to every position. First, see if it's Alice or Bob's turn. If it's Alice, I want to maximize the answer, so do it accordingly. Else, I want to minimize the answer and do it accordingly. And then calculate the new mask, see whether it's already calculated. If it's done, continue. If it's not, store that information, move on, add the new distances calculated in constant time complexity because you had already pre-computed the new distances, and so on, so on, so on. This gives you a, you can say n cross 2 power n order, or in worst case 15 into 15 to 2 power 15 order, which is not very large. All right. And this fully wraps up our fourth problem also, as well as our PCD. So I hope you were able to understand this problem and you liked the video. Thank you for watching.